I enjoyed a lot solving this contest, regardless the stock that I have on problems J. Problems J hits different, and H. Don't blame me. Reading the tutorial or seeing the other guys' videos, it doesn't help me a lot because this guy doesn't explain clearly how come the solution. Certainly because they are smarter than me, and the solution seems obvious for them. If this was happening to you, just bear with me, guys, and see my presentation where I explain clearly the solution of every problem in detail. Enjoy watching, guys, and happy coding. Let's start with the problem A, love story. This is the problem statement. We are given a string S. We want to compute the number of indices where a string S differs from the string Codeforces. S is consistent of exactly 10 lowercase Latin characters. Let's take an example here. If S is equal to the string Codeforces, and our string, we have the string to compare with it, Codeforces. Of course, we need a counter here. Initially, it's equal to 0, and we start by the first character of the first index. We have the same character at that position, C. So we go to the next index, which is 1. We start by 0, and index 1 we have O. We have the same character. We go to this next index, which is 2. We have O and the string S, and D and the string Codeforces. So are not the same. So we add 1 to the count. We go to the next. There are different 2. We add the counter, it becomes 2. We go to the next, we have F in the first string and F in the Codeforces. Nothing happened here. We have O, we have R in the next index. We go to the next index. We have SC, not the same, so we add 1 to the counter, it becomes 3. We have EE in the next index, in the next position, and in the last position, the next index, we have Z and S, so counter will become 4. As you see, it's very simple to code. We can consider this problem like a warm-up problem. We have here our code. We have to give this string S, and we go to test it with the string Codeforces. So we have our counter is equal to 0 initially, and we run over the 10 position from 0 to 9. As you know, in C++, the indices of a string start from 0. So we have to compare S, the string S, the given string S at position I, with the string Codeforces, it's called TS here, and the same position. If they are not the same, are different, we add 1 to the count. And finally, at the end, we return that count. As you see, it's very easy to code and very easy to understand. Problem B, blank space. This is the problem statement. A blank space is a segment of consecutive elements consisting of only zeros. You are given a binary array A of n elements. A binary array is an array consisting only of zeros and ones. Our task is to find the length of the longest blank space. In this problem, we're going to manipulate an array, one-dimensional array. Let's take this example to understand the logic behind the solution. We have this array, and we need two variables. L to compute the length of the current blank sequence, and mx equal for the maximum length found until a specific point. Let's see if first initially we have to initialize the two variables to 0, and we start by the first element at index 0. We have 1. What can happen here is not a blank space. Then we have at position 1 we have 0, so we increment, add 1 to L, to the length of that sequence, and maximum becomes 1 because we found a sequence of length 1 until this position 1. So we go to index 2 and we have 0, we have a blank space, so L becomes 2 and the maximum also becomes 2. And this position, the position 3, index 3, we have 1. It's not a blank space. What will happen here? L will be returned to 0 because the previous sequence is finished. It is of length 2. So until now we have the longest blank space is equal to 2. We go to the next position. We have a blank space. We have 0, so we have 1 here. Now the maximum between that sequence at position 4, the length of the blank sequence at position 4, and founded the previous computed blank sequences, the maximum is equal to 2. We have found a sequence of length 2. Until now we have the sequence of length 1. We go to next position, we have a blank space. Also we have 2, so the maximum is still 2. Now we go to the next position, we have a 0, so the length of that sequence is 3. Now the maximum will change because we have found another sequence, blank sequence, larger than the previous one. So we have to update the maximum. And that position we have 1 is not the blank space, so it returns to 0. Why we return 0 is because maybe there are another blank space or another sequence or blank space after that one, so we have to recompute it. So L is equal to 0, and we recompute that sequence, the length of that sequence. A become 1 because we have 0. At 9 we have 0, 2, it become 2. So that sequence is equal to 2. But we have found, previously we have found a sequence of length 3. So our largest blank sequence or longest blank sequence is equal to 3. The code, we have this code here, the C++. If you understand this logic, it's very easy to code. We have to initialize L and maximum, L to compute the current length of the blank sequence, and the maximum to compute the maximum blank sequence found until that position. We run over the array from 0 to n. If we have a blank sequence, a blank space, which is I equal to 0, we add 1 to L. Otherwise, else L is equal to 0. We update L to 0 and update L to 0. After that, we compute the max between, we update the maximum between the previous maximum and the computed or pre-computed L length of that black sequence at that position I. At the end, we return the maximum found or the array. Problem C, Mr. Perfectly Fine. The problem statement. Victor wants to become Mr. Perfectly Fine. For that, he needs to acquire a certain set of skills. More precisely, he has the 2 skills he needs to acquire. Victor has N books. Reading book I takes him MI minutes, and will give him some, possibly one, possibly none, of the required 2 skills, represented by a binary string of length 2. What is the minimum amount of time required so that Victor acquires all of the 2 skills? If we try to understand this problem, Victor needs to get 2 skills. He have M books. Will give him some, possibly none, of the required 2 skills. He can read a book in an amount of minutes. The book I input format, MI, SI, which MI is the number of minutes that Victor needs to read the book I. SI, it's a binary string of length 2. Sij is equal to 1 if reading book I acquires to Victor skill 1. Sij is equal to 0 otherwise. We want to compute the minimum amount of time required so that Victor acquires all of the 2 skills. Let's take this example. We have 4 books to read. Victor has to read these 4 books. We want to compute what's the minimum amount of time required that Victor acquire the 2 skills. He can read the book, the 2 minutes book that requires to Victor skill number 2, because we have 0, 1 here, so the skill number 2 is required by this book. He can read the book 1 minute book that acquire to Victor the skill number 1, or he can read the book, the 5 minutes book that acquires the 2 skills. So if he must read these 2 books together to acquire the 2 skills, 0, 1, 1, 0. Total minutes of that to read these 2 books is equal to 3. Or he can read only the book, the final book, the 5 minutes book. The total minutes is 5 to acquire both the 2 skills. So the minimum here is 3. Let's take another example. Let's take this example. He can read the 3-minute books, the 3 minutes book and the 5 minutes book, 0, 1, 1, 0, to acquire the 2 skills in the total time of total time in minutes is equal to 8. He can read also the 3 minutes book and the 1 minute book. We have 4 minutes here. He can read the 2 minutes book and the 1 minute book. We have 3 minutes to read these 2 books. Or the 2 minutes book and the 5 minutes book. So the answer here, the minimum here, 3. So reading these two books. How to resolve this problem? We are sure that we have the 3 kind of books that give skills. Skill 0, 1, 1, 0, 1, 1. We will not the book that give no skills 0, 0. We don't need it. So we have to interest to these 3 books that give the 3 skills. We're going to create a map with keys are the 3 skills and values are the minimum amount of minutes. We initialize this map to 0, 1 plus infinity, 1, 0 plus infinity, and 1 plus infinity the first time. And we update every book I skill by the minimum to the previous book I skills to the number of minutes of that book at the current MI. And the answer will be the minimum between the sum of the minimum of 0, 1 plus 1, 0 and the minimum of 1, 1. We go to return -1 if the answer is greater or equal to plus infinity, so we have no change here, or return that answer otherwise. Let's take an example. For example, we have these 5 books. Initially, we have this map, the skill 0, 1, the book that give the skill 0, 1. Initially, we have plus infinity. The book that give the skill 1, 0 plus infinity, and the book that give the skill 1, 1 plus infinity. So we take the first book. The first book give the skill 0, 1. The time required to Victor to read this book is 3 minutes. So we update 0, 1 by 3. We go to the next. We don't need this to skip it. We go to this book. Victor has to read this book in 5 minutes. Needs 5 minutes to read this book. So we update 1, 0 by 5, as you see here in the map. We go to the next. We have this book acquire to Victor the skill number 1, same as this book, 5 minutes. So we have to update this because 1 is less than 5. We go to the last book. We have 0, 1 here, and we know that we have found the book. We have a book on our list that gives the skill 0, 1 in 3 minutes. But here we have this book give the skill 0, 1 in 2 minutes. So we have to update 0, 1 here to 2. So our answer will be the minimum to acquire the skill 0, 1, found the minimum, plus the minimum to acquire the skill 1, 0, and the minimum between this sum and the minimum to acquire the skill 1. So we have 2 plus 1 plus infinity. So we have 3 here in this case. Let's take this example. Same here. We initialize the map to infinity for the 3 skills. We go to 3. Sorry. We go to book, the 3 minutes book 0, 1. It gives the skill number 2. So update it to 3. This book we skip it. We go to this book. It acquire the skill number 2 in 5 minutes. So we keep 3 here because this we have previously found this book in 3 minutes. This book gives the skill number 2 0 because we have 1 here in 1 minute. So we have to update 3 here by 1 because it's less. And we have this book in 0, 0 with keeping. So as you see here, it's very clear that Victor cannot have the two skills using these books because we have only these books given only the second skill. So the answer will be 1 plus infinity, the sum of those two minimum plus and infinity. So the answer is equal to infinity. So Victor, we output -1. Victor cannot have the two skills. The code here, we initialize the variable called inf to infinity with a very big number, as you see here. We initialize the map of the three skills to that infinity, and we run over all the books. We read the amount of minutes and the skills. If the skills is different to 0, 0, because we don't need 0, 0 here, we update the minimum of that skills. So many sorry guys. Minimum of S is equal to minimum of S, the previous minimum, and the current minimum, the current amount of minutes. So the answer, as we have seen in the in the presentation, is the minimum between this sum of these two and this one. Problem D, gold rush. Problem statement. Initially, we have a single pile of n gold nuggets. In an operation, we can do the following. Take any pile and split it into two piles so that one of the resultant piles has exactly twice as many gold nuggets as the other. All piles should have an integer number of nuggets. Here we have one possible move to take a pile of size, this one, and split it into piles of size 2 and 4, which is a valid operation because since 4 is twice as larger as 2. Can you make a pile with exactly m gold nuggets using 0 or more operations? Let's try to understand this problem. If we have first of all, we have a pile that contains 6 gold nuggets in green here. And we want to find if we can make a pile of size 4 using, of course, the split principle given in the problem statement. We can split this pile into 3, 3, but this is not a valid operation because we have 3 is different from 2 times 3. 3 is the size of this pile, for example, and the other 3 is the size of this pile. So this operation is wrong. We have to do, we can split this pile of 6 into a pile of 4 and a pile of 2. So since 4 is equal to 2 times 2, this we have a operation, a valid operation. So, and we have 4 nuggets here, which is equal to m, as you see. So we can return yes. We can split this pile of 6 until finding a pile of 6 4. What's the logic here? First, we have a pile of size n. We have to split it into 2 piles of size x and of size y, such as we have to make sure that x plus y is equal to n, of course, and the condition must be y is equal to 2 times x. Okay, so we can this is a system of equations. We have two equation here. We can resolve y is equal to n over 3. So x is equal to n minus 1. It's very simple to understand. It's a simple math here. You can do it by yourself. And recursively, we have to recursively solve x and y until the base case we find n is equal to n, or n is less than n, or 3 is not divide n. This is our pseudocode for the function. We have to give to the function as parameters n and m. The base case is we return true if n is equal to m. We return false if n is less than m. It's very obvious, it makes sense. Or 3 not divide n. Otherwise, we compute y, we compute x, and we solve. This is the result. We solve x using m, or y using m. If this one of them is true, so the answer will be true. Let's take an example here. For example, if n is equal to 27 and m is equal to 4, so we can split it by 18, and 18 first. We're going left for a few long, and 18 we can split to 12. So because 27 is divisible by 3, 27 by 3 is equal to 9, and we have 2 times 9 here to find 18. Same for 18. 18 by 3 is equal to 6, and here we put 2 times 6 here, which is 12. 12 is divisible by 3 is equal to 4, so we can put 8 here. 8 is not divisible by 3, so we return false. We come back to 12, and we have the other side of the, we have y now at the other side of 8 is equal to 4, because 12 times over 3 is equal to 4. 4 times 2 is equal to 8, so we have found 8. We return false because 8 is not divisible by 3. So the other side is 4, because 8 is equal to 2 times 4. So we have found here 4, which is equal to m. So we return true. So at this point we have false, or true. We have true. We go back to 18. The other side, or the right side of 18 is 6, because we found 12 here. So the other side is 6. 6 is divisible by 3 is equal to 2. So the other side is equal to 2. We return false here because 2 is not divisible by 3. And we have 4 here. 4 is equal to m. We return true. False or true, we have true. And we have to return the true to the previous code. True or true is equal to true. And we come back to, we backtrack to 7. 27 the other side is 9, because we found 18 here. 18, so we have 9 here. 2 times 9 is equal to 18. 9 is divisible by 3 is equal to 3. 3 is divisible by 3, yes, is equal to 1. 1 is less than 3. we return false. We come back to 3. 2 is less than 3. We return false. So we return false here. We come back to 9. 9. The other side of 9 is the 6 because we have 3 here. 6 is divisible by 3. The answer is yes. But here, no need to pre-compute 6 because it already computed here. So we return true direct. No need to pre-compute. This is because this memorization. So we return true. So false or true, return true. So at the end we have true or true is equal to true. This is the code. We need the memo map here to store the pre-computed result of any number and the recursion here. So as we have said, the parameters we give n and m, of course, and we can use this. This n parameter outside the function. It's the same. If n is equal to m, so we return true. This is our first base case. If we found n and the memo, so return. No need to pre-compute it, to recompute it. So because it's already computed. If n is less than m or n not divisible by 3, return false. We compute y and x as we have seen in the previous slide. We return for x the result of x using the recursion here. For x, n becomes x. And same for here, n becomes y. And at the end, if this call is ended and this call is ended, we return the or operation or logic operation between these two results. This is we can use recursion here and memorization to optimize the runtime. The next problem E-Lex. This is a problem statement. You can read it to understand the task, or you can follow me in this quick explanation. You are given an m times n grid of non-negative integers. The value aij is always greater or equal to 0. Represent the depth of water at the ith row and jth column. We can only move up, down, left, or right. The volume of the lake is the sum of depth of all the cells in the lake. Find the largest volume of the lake in the grid. As you see here, let's take this example. The lake here is contains different parts because here we have empty space, or whatever you call it. Let's take this part. You can take this part or this part. So we have the maximum of 11, which is the sum of this one, 5 plus 4 plus 1 plus 1 is 11, or the sum of these two, 3 and 5 is 8, or the sum of all these is 24. So here, the maximum is 24. The largest volume of the lake is 24. What technique we can use here? We can use depth first search, known as aka DFS, or breadth first search, aka BFS. In this case, I am going to use DFS. DFS is the most well-known algorithm to explore a graph. If you don't know what's DFS in DFS guide, you can search it on the internet and found thousands of tutorials that talk about this topic. Its time complexity is big O V plus E, which V is the number of vertices in a graph and E is the number of edges. We can use this technique to compute, to know the connected component and component of the graph, to know the connected components on a graph, find articulations points or bridge, determining connectivity of a graph, etc. It's the principle of the DFS is the go in depth, regardless of what edge to take, and backtrack when we reach a dead end or a visited node. Let's take it. If we have this graph, and of course I have to give to this to algorithm, to DFS, a starting vertex or node. Let's say that we're going to start by 0. The green ones here mean they are visited. So to not we have not to revisit that node in the future. So 0 is visited here. We can go to 5 or 7. Let's take 7. Whatever you take here. We go to 7. 7 is visited. From 7 you go depth to 9 or 13. That's 9 here is visited. From 9 we go to the only choice, so the only option here, we go to 12. 12 is a dead end, as you see, so we backtrack to 9. From 9 we will continue visiting the other nodes from 9, because we have 2 here. We have to visit. We visit 2. And from 2 we go to A. A is a dead end. We backtrack to 2. From 2 we backtrack to 9. And now, for now, 9 is completely explored. So we backtrack to 7. From 7 we can go to 13. 13 dead end. We backtrack to 7. 7 is completely explored. We backtrack to 0, the starting point, but 0 is not completely explored. So we go to 5. From 5 we can go to 1. From 1 we go to 3. 3 is the dead end. We backtrack. 1 is completely explored and is visited, of course. We go back to 5. 5 we go to 6. From 6 we can go to 10. From 10 we can go to 4. 4 we go to 6, but 6 is completely explored and visited. So we backtrack, as you have seen, the node visit area visit node. We go back to 4. We backtrack from 4 backtrack to 10. From 10 we go back to 6. From 6 we backtrack to 5. And from 5 we backtrack to 0, which is our starting point, and it's completely explored. As you see, the node 11 is not visited because it's completely disconnected from the graph. This is the pseudocode, the general pseudocode of DFS. We have to represent a graph and the adjacency list or adjacency matrix. If you don't know what's a graph, it's the occasion to read a little bit about the graph, but we're going not to use it in our solution for this problem. So we can, maybe later you can read this. We need an array visited of size n of Boolean, name the number of nodes here n. We initialize visited to false, and we DFS node, the function. It will take as parameter the node to visit, the current node to visit. If that node is visited, we backtrack, we return to the previous call. Otherwise, we mark that node as visited, and we get all the neighbors of that node. And for each neighbor in the list of neighbors, we go in deep DFS to that neighbor. Of course, in the main program, we call DFS, and the starting point is here. I took 0. In our problem, we have a matrix, not a graph. So we will consider each cell of the grid as a potential starting point of the to perform a DFS. So because we don't know here what's the starting point of each part of the lake, it could be any cell. So each cell here is a potential starting point, and perform a DFS from that starting point. No need to explore visitor or empty cells as you have seen. Let's represent this as a graph because it's more simple to understand. Of course, in our solution, we are not going to represent this as a graph, adjacency list or adjacency matrix, because no need. We can use the matrix itself. So we will see how. We can say that the starting point is at 0, 0. We have 5. This graph, it is a representation of this matrix. Don't forget. So at 0, 0, we have 5. This is our first starting point. So we can, the result of the FS for now is equal to 5. This is a visit point. We can go, for example, to 1, 0, line 1, column 0. We have 1. So DFS, we add 5 plus 1, we have 6. We can go to line 2, column 0, we have 0. At this point, of course, we have to backtrack because we have said in the problem statement, only we want to compute the volume of the part of the lake. The empty parts are not counted. So we have 0 and empty depth. There's no depth, there's no water here. We mark it as visited and we backtrack to 1. From 1 we can go to 1, 1, which means row 1, column 1. We have 1 here. We update the DFS result from 6 to 7. We can go up to 0, 1, we have 4. So we mark it as visited and we update the DFS. We have 11. From that cell, we can go to 0, 0, but 0, 0 is visited. We backtrack. We can go to 0, 2. We have no water. We have an empty space there. So we mark it as visited and we backtrack. From 0, 1, we can go back to 1, 1. We have to go back to 1, 1 because here it's all this cell is completely explored and visited. So we backtrack to 1, 1. From 1, 1 is not completely explored, so we can go to 1, 2. Row 1, column 2, we have empty space. So we mark as visited and we backtrack. And we go, it's not completely, as you see, is not completely explored. So we go to 2, 1, we have an empty space 2. We mark as visit and we backtrack. So from that, we can backtrack to 1, 0, we backtrack to 0, 0, and this is the end of this part. We have 11 here, so we have to put it in the answer for now is the maximum between 0 and 11. We have 11. And we go to the next starting point, but this is a visited cell, so no need to be a starting point. We put as visited cell, it will give me the same result. Next starting point, 0, 2, is not the starting point because it's visited. We go to the next cell, 0, 3 is not visited, so, and is different to 0 as you see. Here, not visited and different to 0, so we can consider that a starting point. We start DFS from that point now, from that cell or that node. Is equal to 3, so we update the DFS will give me 3. We can go down to 1, 3, it's 0, so we backtrack. We mark it as visit and backtrack. From 0, 3, we can go to 0, 2, but it's visited, as you see, so we backtrack. From 0, 3, we can go to 0, 4, which we have 5. So DFS, we add this to DFS. We mark it as visit first, and we add this to DFS is equal to 8, 3 plus 5. From 0, 4, we can go down to 1, 4. Is an empty space, so we mark it as visited and we backtrack. 0, 4 is completely explored, so unvisited we backtrack. So we backtrack to the 0, 4, 0, 3 as you see, which is our starting point. So now we compare this result to 11. So 11 is still the maximum, so 8 will not be taken here. We maintain 11. We go to the next starting point for DFS is visited, so no need to be starting point. 1, 0, same for 1, 0. Starting point, this is starting point, no, because it's visited. 1, 2 is not a starting point because it's visited. 1, 3, same. 1, 4, same. 2, 0, same. 2, 1 is not a starting point because it's visited. 2, 2. 2, 2 is not a starting point because it's equal to 0. No need to start DFS from this cell. We go to 2, 3. 2, 3 is not visited and is different to 0, is equal to 5, as you see. So we can consider this starting point for DFS, and we update the result of DFS will be 5. We can go down to 3, 3 is equal to 6. So we add this to the DFS result. We mark it as visited and we add this. It will be 11. We can go from 3, 3, we go left to 3, 2. And mark it as visited and we add this to DFS. It's 14. We can go left to 3, 1 is equal to 2. Is not visited, is different than 0, so we can add this to the DFS and mark it as visited. 3 is, we can from 3, 1 we can go up, for example, to 2, 1 is equal to 0 and is visited. So we backtrack. No need to do this cell. And from 3, 1 is not completely explored because we have 3, 0 here. We go left to 3, 0. We have 1 there, so we add it to the DFS, mark it as visited, and we add it to DFS, becomes 17. From there, from 3, 0, we can go up to 2, 0, it's visited, so we backtrack to 3, 0. 3, 0 is completely explored, we backtrack to 3, 1. 3, 1 is completely explored, we backtrack to 3, 2. 3, 2 is not completely visited, we go up to 2, 2. 2, 2. Is not visible but is equal to 0, so no need to put it on DFS or to explore that. We backtrack to 3, 2. 3, 2 is completely explored. We come back to 3, 3. 3, 3 is not completely explored. We go to 3, 4 at the right. We have 1 there. We add this to DFS and mark it as visited. And from 3, 4, we can go up to 2, 4. We have 6. So we mark it as visited and we add it to DFS. We have 24. From 2, 4, we can go up to 1, 4. It's visited, so we backtrack. From 2, 4 is not completely explored, so we go to 2, 3. 2, 3 is visited, so no need to add this to DFS there. So we backtrack to 2, 4. 2, 4 is completely explored. We backtrack to 3, 4. From 3, 4 completely explored, we backtrack to 2, 3. 3, 3 completely explored. We come back to 2, 4, which is our starting point, and this is the end. And at the end of DFS, we I think I have. Of course, you see here before the answer, I forget this. We have 2, 3 is not completely explored, so we can go right. And this one is normally is visited here because from 3.2 is visited from 3.2. I think is the mistake here. So on the, of all case, in that case, we backtrack. We can go up to 1.3 is visited, so we will come back to 2.2.3. Now our starting point is completely explored. So we update our maximum, our answer here to the maximum between the result of DFS from that point and the previous result, which is 11. So now the result will become 24. And we go to the next starting point. It's visited. This one is visited. No need to be explored. This one is visited. This one is visited. Is visited. And is visited. As you see, this is the code. First, I'm going to initialize a map of moves. So to be used when I perform a DFS to go up, down, left, or right, as you see here. Then, after reading the M and N, the size of the and read the lake, I have to initialize the map visited or to false. I use here the pair ij, which means, for example, here 0, 1 is visited, 1, 1 is visited, etc. So every node in the beginning is not visited. And we have called the function solve, which is take the lake and visited. Solve here is our answer initially at equal to 0. Every node, every cell is potentially a starting point. Is a potential starting point. If that starting point is not visited, if it is not visited, or let's take the inverse here, if it is visited or the lake at that point is an empty space. We continue, we go to the next, which means here we go to the next starting point. Otherwise, our answer is the maximum between the previous answer and the result of the DFS from this starting point. Okay, let's see DFS now. Of course, I will give to the DFS as parameter the lake, of course, but the more important part is here. I will give the row and the column. As you see here, in the beginning, I will the main program, we will call the DFS using the counter I and j of the loop. Here. First, we have 0, 0, and then 0, 1, etc. Or maybe any couple of I and j here at condition not visited, and the lake at that position is not 0. So, given any row and any column here, we have to be careful. If we must be in the grid, not outside the grid. If we are outside the grid, return 0. How to know if we are outside the grid or no? Must one of this condition is equal to 2. Row, this one, row is greater than n minus 1, or row is less than 0, or column is greater than m minus 1 because it's size of column m here, or column the column and the number of current column is less than 0. So we are at that if one of these conditions is equal to true, that means we are outside the grid and return 0. If is visited, the row and the column, the current row and the current column of this call of the DFS is visited, return 0, 2. Otherwise, put it as visited, this current column and current row, and if the lake at this position row and call is equal to 0, we backtrack to also return 0. Every time we have a return, we backtrack. Otherwise, the answer will be is equal to initially before the go and deepen with DFS. Initially is equal to the value of that of the depth in the lake at the current row and column, and we have to DFS the 4 directions. From that row column we go up, down, right and left, I think. Okay, of course we compute the row, the next, if we can say the next move, the row on the next move, the column on the next move, and we DFS, and we call DFS again. And it will be tested if this row and column satisfy all these conditions or not. Okay, I think this is all for this problem. The problem F, forever winter. Let's see the problem statement. A snowflake graph is generated from 2 integers x and y, both greater than 1, as follows. Start with one central vertex. Connect x new vertices to this central vertex, and connect y new vertices to each these x vertices. Like we see in this example below in the snowflake graph for x equal to 5 and y is equal to 3. This is the start vertex, and we have from that start vertex we have 5 new vertices because x is equal to 5, and for each 5 vertices we have 3 new other vertices because y is equal to 3. Our task is to, given a snowflake graph, our task is to determine the values of x and y. As you see here, given we will give you a graph representation, your task is to compute x and y. Because we know that from the problem statement, we know that we have a start vertex. From that start vertex, we have x vertices, so x edges. And for each edge in green here from that start vertex, we have to connect, I call it a central vertex, so we have many of central vertices here. And for each central vertex, we have y we have to connect y new vertex. So we can have this table here. We have to compute the degree of the nodes. What do you mean the degree? The degree is simply, we can say that the number of edges connected to that node. This is the degree. For example, this node is degree 6. Okay. So we have the start vertex is the degree x, because from that start vertex we have x vertex in green. And the center vertices now, how many center vertices we have? We have x, because makes sense, because we have x edge here, and at each edge we have to connect another vertex in yellow here. 1, 2, no. So the number of center vertices is equal to 2x. So we have x center vertices. The degree of each one is equal to 4. Okay, is equal to, sorry, is equal to y plus 1. No, from where I said 4 here. The degree, so the degree of x center vertices is equal to y plus 1, because here we have each center vertex y edge to connect to the other vertices, and don't forget the edge that coming from the start vertex. So if this vertex edge is equal to y, so we have plus 1 here to add to that, the degree of this center vertex. Okay, then we have the end vertices here. How many end vertices we have? We have, for each center vertex we have y and vertices, and how many center vertices we have? We have x. So in total we have x times y and vertices. So x, y vertices of degree 1. Each one is of degree 1. So we can get this table. We have vertices. We have one vertex of degree x. We have x vertices of degree y plus 1, each one, and we have xy vertices of degree 1, each one. We can take an example to understand what happened here. As you see here in this picture, this image, we have a starting vertex of degree 2 in green. So x is, because x is equal to 2. So we have one vertex of degree 2. So because we have x is equal to 2, so we have 2 center vertices. We have 2 center vertices. The degree of each one is equal to 5, because y is equal to 4. From that center vertices we have 4 new vertices, new 4 edges, and don't forget the edge coming from the starting vertex. So we have each one is a degree 5. 1, 2, 3, 4, 5. Okay. And the end vertex we have 8, as we have said in the previous slide, x times y. We have a degree 1, each one, degree 1. 1, 2, 3, 4, 5, 6, 7, 8, each one of degree 1, as you see in the image. So we have this table for this graph. Let's take this another example here. And we do the same thing here. We have one starting vertex of degree 3, which is in green here. Then 3 center vertices of degree 3, each one. 1, 2, 3, each one of degree 3, sorry. 1, 2, 3, each one, 1, 2, 3, 1, 2, 3. Okay, and we have x and vertices, x times y and value, which means 6, 1, 2, 3, 4, 5, 6 of degree 1 each one. But as you see here, we have here the same degree for these 2 type of vertices. Okay, we can group them together. So we have here 4 vertices, each one of degree 3. What we can say, so in general, we have a graph as described in the problem statement. From that graph, we can compute that we have 1 vertex of degree x, vertices of degree y plus 1, xy vertices of degree 1. We have in each case, as we have seen in the previous slide, previous example, if x is equal to y plus 1. Like here, x is equal to y plus 1. Okay. So we can group them together. It's very simple to prove. If x is equal to y plus 1, we can say that we have x plus 1 vertices of degree x, and the other remain the same, x times y vertices of degree 1. Okay. We can say if x is equal to y plus 1, this table will change. We can put here y plus 1, we have y plus 1, y plus 1 here, and we have x plus 1 here because we have 1 vertex. So x plus 1 vertices of degree y plus 1. So the problem now is reduced to compute the degree, the number of vertices, how many vertices have a certain degree, x or y plus 1 or 1 or x and 1. Okay. So we take the number of vertices sorted in an array. This is the number of vertices. In this case, of course, we have 2 cases here. In this case, we have this array. And in the other case, this one, we have this array. We sort them to have this representation. We are sure that if we have of course a graph like described in the problem, we will have this content of the table 1 x xy. We are sure that x is greater than 1 and x times y is greater than x. Same here, we are sure that x times y is greater than x plus 1. So we sort them like this, and we are sure now that if we have this case, the first case here, we are sure that the value of x is at v1 here. And of course, if we have the value of x, we can compute the value of y because we have this number xy. Same for the other case. We can say that now, if the length of v is equal to 3, the first case, we can compute x is equal to v1 and y is equal to v2 over v1. Otherwise, which means the size is equal to 2, we have x is equal to v0 minus 1 because we have x plus 1 here. We can compute y using this value here, v1 over v0 minus 1. Let's take another to understand how it works. If you have this graph representation, first we have to compute the number of degree of each vertex. For example, here, if we are at the edge 2120, which means the vertex 21 and the vertex 20, we go to the map, we add 1 to 21 and we add 1 to 20. If we are now at 520, we go to 5, we add 1, and we go to 20, we add 1. Become 2. 1320, we go to 13, we add 1, and we go to 20, and we add 1, it become 3. 1, 3, we go to 1. Vertex 1, we add 1. This is the degree of 1 for now. And go to 3. This is the degree of vertex 3 for now. Of course, we do the same for the others. It's very obvious now. It's very clear. Let's go quickly. Okay. Okay. At the end here we have 3. Now we have computed the degree of each vertex in the graph. Now we have to compute. After this, we have this result. We have to compute how many vertex have that degree. For example, here, how many vertex have the degree 1? How many vertex have the degree 4? And same here, how many vertex have the degree 5? We will have this table. Here the degrees and here the vertices. So, and for this graph, we have 15 vertices of degree 1, 5 vertices of degree 4, and 1 vertex of degree 5. We have this representation as we have seen in the beginning of this video. So we can say that we can take only the number of vertices now, 15, 5, 1, which mean xy, x1. We have to sort it to be sure that we have 1 at the beginning, x at the middle, and xy at the end. Okay, and we can now compute x and y. We know that x is equal to 5. This is our x. Here. Okay, and because we have x times y is equal to 15, we can compute y. It will be is equal to 3. Okay. The code. So this is the map. This map will compute the degree of each vertex. We read u and v from input. Node 1, node 2, to vertex 1, vertex 2, and you add 1 to each one in the map. Once we have this map, we can compute the number of vertex or vertices that have a degree d in the first map. So we will have at the end a map of size 3 or a map of size 2. We put them in an array. We put the results, the value of the map counts 1 here. We put it in the array V. Why the second? Because as we have seen in the previous slide, this one, we have the degree of this map counts 1. The key are the degrees, and the values are the vertices. Because this is what you have. Because we have here in the first map count how many vertex has the degree 1. So we take 1 here. We take 1, for example, and we compute. We have 1 here. And then we have to, this is node, we have 3 here, 4, etc. So we compute the number of vertices that have the degree 1. So the values are the vertices, because that's why we choose the second p.second for the in C++, which is the value of the map. You know that a map in C++ or the dictionary, it has a key and a value. Okay, a key and a value. To access in C++, to access to the key, we say p prime first. Here, for example, for every pair, this is a pair in the map counts 1. We have key p prime first. value p.second. So we put on the table p.second, which is the number of vertices. We saw them, and as we have said in the previous slide, we check if the size of the array is equal to 3 or not. We use the same formula. I hope this video is helpful for you guys. Thank you for watching. Problem G, it's different. This is a very interesting problem. I really enjoyed this one. Let's see the problem statement. In a carnival game, there is a huge pyramid of cans with 23 rows, numbered in a regular pattern as shown. You throw a ball at the pyramid, and it hits a single can with number and square. This causes all cans that are stacked on top of this can to fall. That is, can and square falls, then the cans directly above and square fall, then the cans directly above those cans, and so on. For example, the picture above shows the cans that would fall if can and square is equal. What is the sum of the numbers of all cans that fall? Okay. If I take the same example here, if I hit 9 square, the cans above 9 square will fall, and the cans above these cans also fall, and so on until the can number 1 is the end. So we have to pre-compute the sum of this numbered cans, which is 156 here in the example. All this can will fall as we have seen. So the task, we give you this pyramid and the number n, not n square, n, where hit by the ball. You have to compute all the sum, all the fallen cans. Okay. My first thought was to present the pyramid of 23 rows as a graph. This is my first thought. Directed graph, for example, here. For this example on the left here, I represent as a graph here, as you see in the image. Directed graph. Why a directed graph? To know which can is connected to another can. Okay. For example, here, if I hit 9, all these can in red will fall. From 9 in the graph, we can perform abvious. If we have this particular graph, we can perform abvious starting from 9. We go to 5, for example. From 5 we go to 2. From 2 we go to 1. 1 is a dead end. We backtrack to 2. All the nodes of 2 are explored. We come back to 5. From 5 we go to 3 because 3 is not explored. From 3 we go to 1. 1 is explored. 3 is explored. Don't forget, as a directed graph, we cannot move from 3 to 6. And we'll come back to backtrack to 5. From 5, we backtrack to 9. We go to 6 from 9 because not explored 6. We go to 3. 3 is explored. It's visited. Same for 6. We can backtrack to 6 is visited, explored. 9 is completely explored, so this is the end of our DFS. As you see, the part of the graph in gray here give me the same result of the problem. But the problem here is the number of nodes in the graph. It's a very huge number, as you see. We can compute it, of course. we have this number 2 million number of vertices, 2,074,000 and 276. 47, sorry, here 2,047,000 and 276. The number of edges, as you see, is here. And as we know, the DFS, so to perform for each given n, for each query, we can say that we perform DFS in B plus time complexity. That's why when I submitted this code, it gave me a TL, time limit exit. As you see here in the image. Here I build the graph, no matter how, not because we will not use this solution. This is I perform a DFS for a given node, and here for each given n and the problem test cases and the test cases, we compute given to function solve n solve. So as its node, we perform that DFS on that node. Even I used the memorization to minimize the runtime execution runtime, but it didn't work. So, guys, I was completely stuck on this point. To be honest with you, I didn't figure out the data structure or the solution or the idea behind this, how to solve this problem. So I read the tutorial, and directly it gave me a clue. Skip this one. The idea is to, if we draw the pyramid, the given pyramid and the problem. So it's like this, like a diamond, not a pyramid. It will be like this. And if we rotate it counterclockwise, it will be like this. And we can see this is a matrix, and we just perform a 2D prefix sum. This is the clue. This is the light that gave me the answer. I didn't see the solution for this one. I just read the tutorial. The idea of fate, guys, that I made a video, or I made a complete lecture in range query, and I made in this lecture I made a video that deal with the topic 2D prefix sum array. But for this problem, I didn't see it. You will find this in the if you don't know the 2D prefix sum array, you will find the video link in the description below. So we will pre-compute all answers in a 2D prefix array. We can say that it's constant time because we know the number of rows, which is 223, but we add one here to the matrix, for the matrix. In same time, we have to store in a map all n's answers, all the n's with their answers, because only n is given, not a range here. So we're not given a range from a point A to a point B, compute the sum. No, it gives me only n, and we have to know the sum. So we have to find a way to store the answer of each n. Okay, using, of course, the 2D prefix array. Then we will see how it works. The logic. So we have this matrix. Let's say that here we have a matrix of size 5 times 5. So the 2D prefix array will be 6 times 6 because we have to add the zeros at the first line, row, and then in the first column. Again, guys, if you don't know what is a 2D prefix array, you can see it before. Continue with this video. You can see it below in the description and understand how the 2D prefix array work. So for each range here, we will compute the sum. For example, here, if I take this range is computed here. This one, 29. That's 5, 25, 25 plus 10 is 35. 35 plus 4 is the 39. Okay. And as I've said, for each n, we will store the answer. For example, for n is equal to 1, the answer is 1. For t, the answer is 10. The sum, if we hit 3, the sum of all the following cans, if we hit 6, is 64. The sum of if we hit 9, like a proper statement here, if we hit 9, the sum of all following cans is 165, 56, etc. Okay. Let's see how we will build this for this problem, of course. How we build a matrix like this. We have 1, 3, 6, 10, 15, 2, 0, 2, 5, 9, 14, etc. Let's see this observation. Let's observe the images here. And we will see that for each line in this picture, in this image on the left, for each line number 1, we have 1. Line number 2, we have 2, 3. Line number 3, we have 4, 5, 6. Okay. So for each line, we have a consecutive range of numbers here. And as we have said, if we rotate this image counterclockwise, these lines becomes diagonal. As you see, the diagonal here is not the anti-diagonal. Let's say diagonal. As you see here, diagonal 1, we have 1. Diagonal 2, we have 2, 3. Diagonal 3, we have 5, 5, 6. Diagonal 4, 7, 8, 9, 10, etc. Okay, this is the first observation. How to find the diagonal? This diagonal. If we have a matrix, it's very easy. This is a well-known trick. Just we have to sum the number of column plus the number of row plus column. But here, because we have add 1 to each to the matrix, we have to subtract -1 to find the column 1 here. For example, here, as you see, the diagonal 1, we have 1 plus 1 minus 1. Okay, but all the diagonal 2, we have 2 plus 1, which is a 3, minus 2. And we have 2, we have 1 plus 2 minus 1, we have 2. So here, if we make this formula, we will find all the diagonals. Okay. Observation 2, how now to find these numbers, especially this first one, in the first row. If I take the first line or the first diagonal, we can say that is equal to 1 times 2 over 2. The second row, we have 3 here. We are computing these numbers, don't forget. We have 3, so we have this is diagonal 2. We have 3 is equal to 2 times 3 over 2. For diagonal 3, the same diagonal, 6 is equal 3 times 4 over 2. Same for 10. 10 is equal diagonal 4 times 5 over 2. Same for 15. 15 is equal 5 times 6 over 2. So we have found all this numbers for the first row. Okay, using this formula. In general, also to find the first number on the first line, first row, we use the diagonal plus times diagonal plus 1 over 2. So we can compute this. For the first row, we have 1 here is on the diagonal number 1. So we can say that 1 times 2 over 2 minus 0. We will speak about this value later. For 3 is in diagonal 2, as you see. So 3 is equal to 2 times 3 over 2 minus 0. 6 now. 6 is in diagonal 3. So 6 is equal to 3 times 4 over 2 minus 0. For 10 is in diagonal 4. It's 4 times 5 over 2 minus 0. Same for 15. 15 is in diagonal 5. 5 times 6 over 2. Now how to compute the second line of the matrix, second row. We add 1 to this value here, because we have to compute the second row, which is the second row, as we have seen. This is the first element minus 1. And then for this row, the first element to compute it minus 2, etc. We will see it. How to compute 2? 2 is at diagonal number 2. So we have 2 times 3 over 2, but minus 1. Because 2 times 3 over 2 will give me 3, which is this number. But here we know that the number in the diagonals are consecutive. This is the largest one, the greatest number on that diagonal. So on the diagonals that directly previous to this and the line immediately previous to this line is minus 1. We subtract 1 to this. Same here. We have 10 here, 9 here, 9, 8 here, 7 here. So we have to subtract from this number minus 1 here. From 10 we have minus 2, 10 minus 3, etc. Okay. So we have 2 for 2 times 3 over 2 minus 1. For 5 now. 5. How to compute 5? 5 is a diagonal 3. So we do the same. 3 times 4 over 2 minus 1. 3 times 4 over 2 is equal to 6, which is this number. But in the previous, we have 5. We have to subtract 1. Okay. Same for 9 and same for 14. Let's see now 4. How to compute 4? 4 is equal, if you understand now the process, is at column number 3. Okay, so we have a 3 times 4 over 2, which is 6, but don't forget 6 is at the first row. So we are computed the number at the last row. Let's say this is the first row. First row here, second row, third row. 4 is at the third row. So we have to subtract 2. Okay, from this 6 minus 1 to find 5, 6 minus 2 to find 4. Okay, Same for the others. Here for 7 and 12. For 7 is at row 7 is at row 4. So 4 times 5 over 2, which is 10. 10 minus 3 to find 7. Okay? Because the number are consecutive and this in each diagonal. So we have computed the first one, minus 1 to find the previous, minus 1 to find the previous of the previous, and minus 1, etc. Okay. So now let's see the simulation of the code of the run, how to code the code to build the 2D prefix sum array. Of course, our array is of size 2024, 2024, but for simplicity here, I will take an array of size, a matrix of size 6 times 6. We start for the first row, first column, we compute the diagonal, which is diagonal 1, which is here. Our v is equal to 0 at the first. We compute n, which is 1. And this formula is for to compute the prefix sum of the original array, original matrix here. Again, for the third time, again, if you don't know what happened, how the formula from where they have the formula, you can see the video on the line below, on the link on the description to that deals with the prefix 2D prefix array. So if I use this formula, I will find the prefix at ij is equal to 1. Let's try quickly what's the meaning of this. We have 1 here. 1 here is the sum of this range. Okay? It's very clear here. Let's go forward. I will explain this a little bit later. We have 1 here. So on this table, we'll store if we hit 1, we have the sum 1. And we go to 2. We have diagonal is equal to 2, v remains 0 because we are computed the first line here. The n is equal to 3, which is this one. So the prefix sum is equal to 10 because 3 squared plus 1 squared is equal to 10. Okay, this one. Three, 10. We go to third column, first row. We compute the diagonal. We have 6 for n, this one. Okay. 46. So 46 there. And for 6, we have 46, which means if we hit the can numbered 6, the can number 6, the sum of all falling cans is 46. Okay. We go to the 4 column. We have n is equal to 10, this one here. So the sum here is 146 for 10. The fifth column, we have 15. 15, the sum all these row is equal to 371. Okay, so 15, we have 371. Now We go to the second line, the second row. So we have to add 1 to this V, because as we have said in the previous slide, the number and the diagonals are consecutive. So we have computed the first row, the second row, all these numbers of each diagonal, the number -1. Like here, for example, we have 3, 2, 6, 5, 10, 9, 15, 14. So we have to subtract 1 from the first row. Okay? We go to the second row, 2, 1, column 1, diagonal is 2. So we compute this diagonal is 2 here. We have 5, which means the range, this range, the sum is equal to 5. Okay? So for 2 we have 5. We go to second column, we have the diagonal is equal to 3, n is equal to 5. The sum and its range is equal to 9, 30, 39. We go a little bit quickly. Okay. Let's take this number, 405. This number is the sum of this range. I think this range. Okay. Let's check together first. I need the calculator here. Okay, that's it, which is 13 times 13 plus 81 plus 36 plus 5 squared plus 9 plus 16 plus 4 plus 1. Okay, is equal to 405. This one. Of course, in the prefix to the prefix array, we will not pre-compute every time the sum like this. We will use the pre-computed ones here. So the sum of this and this cell is equal to the sum here in this array, which is the sum of this one in blue, this one, plus the sum of this one in green. But as you see here, this part, let's change the color here. Okay, let's make it this color. And this part here is computed twice using the blue square and the green square, which is this one. So we have to add this plus this and minus 39. Okay, plus 13 squared. Don't forget this 13 squared. So we compute this using the calculator. 165 56, sorry, plus 119 minus 39 plus 13 times 13. We have a problem here. 39 here, sorry. 39. Okay, the same result as you see. This is the principle how to compute the prefix 2D prefix array. Okay, let's continue with this. Okay, we have here the same principle. Let's make it quickly. This is the code. The code here, given n, we use this I think an array here, map. Use a map for the answer. This is an odd constant time, big O1, because we have compute all the answers here. Using the 2D prefix array, we have p, so the size of the array, and using the same principle that we have shown in the description. Compute the diagonal, compute an n, the prefix, and store the answer of each n. I hope this video is very helpful for you. I really, as I said in the beginning of the video, I really enjoyed this video. I hope that you enjoy too, guys. Problem H. Don't blame me. This is the problem statement. Given an array A consisting of n positive integers, count the number of non-empty subsequences for which the bitwise AND of the elements in the subsequences has exactly k set bits in its binary representation. Let's take an example here. For example, if we have an array of 3 elements and k is equal to 2. These are the subsequences that we can fold from the array 3, 6, 7. We can 3, 6, 7 and 3, 6, 3, 7, 6, 7, 3, 6, 7. This is all the subsequences that we can fold from this array. The AND bitwise result of each subsequence, here we have only 3. This is the binary representation of 3. Here we have 6, only 6. Here we have 7. Here 3 and 6, which is equal to 2. This is the binary representation of 2. This is 3 and 7 is equal to 3. 6 and 7 is equal to 6. 3 and 6 and 7 is equal to 2. Which are of these subsequences which their and bitwise representation is equal to 2? Okay, we have this one because we have 2 set bits here, one here, this one too, because we have 2 set bits. This is no, because here we have 3 set bits. This is no 2 because we have 1 set bit. This is yes because we have 2 set bits, because k is equal to 2, so we have 2 set bits. Same here and no. So at the end we have the number of subsequences that have exactly k set bits in their bitwise and values binary is equal to 2. Is equal to 4, sorry, equal to 4. We can do this by a naive approach, which means we will brute force all the subsequences using bitmask. The number of all subsets or all subsequences of set of an element is equal to 2 power n. We can fold it by 1 left shift n in constant time. And check if the jth element and the subset is. How to check this? First, we left shift 1 by j bits. J is the index of the element aj in the array A. do an and bitwise operation between the subset S, L, and the result found from the left shift. And we check if S and that left shifting of one j bits of 1 is equal to 0. So it means that the j is not in A. Otherwise, j is in A. A second quick example. We have this array, of course. Yeah, so suppose that we want to check if 6 is in the subsequence 3 and 7 or not. Here are all the subsets from the element 3, 6, 7. We can empty set, of course. We have 3. 3 is the number is number 1, 6 number 2, number 3 is 3, 6, number 4, 7, number 5, 3, 7, 6. Number 6, 6, 7, and number 7 is the subset 3, 6, 3, 6, 7. Okay. How to do this? First, we're going to left shift 1 by 1 bit, which means we have 1 here, the number 1. We're going to left shifted by 1 position to the left. So 1 will be here, which means here 1. Why 1? Because 1, we know that 1, all of the other bits are 0 except the first one. We shift this by the position. This is the position of the element in the origin array that we want to check if it exists in the subset or not. This is the 1, 6 is at position 1. So 1 will be at position 1 here, after left shifted by 1 to the left. Okay, which is equal to 2. Then 3 and 7 is number 5. Here, as you see, 15. So this 3 and 7 is number 5 for the subset. So we make 7 and 2, 5 and 2. Sorry, 3 and 7 is number 5. So we make we end bitwise 5 and 2. This is 5, and this is 2. As you see here, the result is equal to 0, which means here, before the result, we interpret the result. We have here 1, 0, 1 in subset 5, which is the 7. The bit at the position 1 is not set, as you see. This is the bit at the position 1 is not set. And here only bit 1 is set. This allows us to check if A1 is equal to 6 exists in T7 or not. So here, the 6 is not in the subset 3 and 7. Of course, we're not going to more in details for this approach, because I get that you see time limit exceeded in test 3. This is the pseudocode, and this is the C++ code. Just this is how to run over all the subsets from 0 to n-1. From 1 to 2 power n. This is all the subsequences. Okay. And from 0 to n-1, this is each subset apart, the elements in each subset. We check if the subset, the element at position j is in a subset I, yes or not. Subset I. If different to 0, so we compute its and bitwise result. And at the end, we check if the number of set bits of S is equal to K, yes or no. If yes, we add 1 to the answer. This S and this variable CNT is for S for the result and bitwise, and CNT for the checking if we have already element in the subset, yes or no. If no, so AJ will be the first element. If yes, so we make the bitwise operation. Okay. Of course, this is not the good solution. The solution here, we're going to use dynamic programming and the I was completely stuck on this problem after getting the TLE. So I read the tutorial. To be honest with you, I understood nothing. Just I have the idea about how it works or how I will implement this, or the logic, the real logic behind this, how they find this. I didn't figure out that. So I saw another tutorials. I search a lot on the net for other tutorials. Say the tutorials are very quickly and use the same idea. They explain very quickly the solution because maybe the solution is very obvious for them. But for me, I didn't understand. I didn't figure out how to find this. So I spent a lot of time to understand the solution for myself. The first thing that is easy to understand is that we have the elements of the array are between 0 and 63. So we can count the number of subsequences that have n value equal to x for all x from 0 to 63, because we can, is limited as you see, it's not very huge. So we can compute all the subsequence for each subsequence, how many subsequences we have for any result and bitwise result from 0 to 63. Let's see how it works. For 3, 6, 7, the first subsequence is 3. And we have 3, 6, and 3, and 6, and the subsequence 3, 6. And we have all these subsequences from 0 to 2, which means from 0 to 0 we have 3. From 0 to 1 we have 3, 6, and 6. And from 0 to 2 for all the elements we have all these subsequences. And first we start by this row. The indices in the rows are the indices of the array 0, 1, 2, the elements. The indices in the columns here are the and bitwise result, which means here, for example, for this subsequence 3 is its result and bitwise result equal to 0? No. Is it equal to 1? Its and bitwise result? No. Is equal to 2? No. The and bitwise result of 3 is equal to 3. So we have one subsequence here, which is 3. Its and bitwise result is equal to 3. We have 3, the subsequence 3. Its and bitwise result is equal to 3. 4, no. 5, no. 6, no. 7, no. We go to the next row for these subsequences. How many subsequences on these subsequences? How many subsequences their and bitwise is equal to 0? None. How many subsequences there and bitwise is equal to 1? None. How many subsequences the bitwise and bitwise is equal to 2? We have just one, which is 3 and 6. This subsequence 3 and 6, its and bitwise between all the elements of 3 and 6 equal to 2. So we have one subsequence. Here, for 3, we have only one, which is 3. Because the n bitwise of 3 is equal to 3. 4 none, 5 none, 6 none. Oh, sorry, for 6 we have 1, which is 6. Okay. For 6 we have one subsequence, which is 6. Its n bitwise is equal to 6. For 7 none. We go to the last row. How many subsequences in these subsequences their n bitwise is equal to 0? None. Equal to 1? None. Equal to 2? We have 2, which are 3, 6, and 3, 7, 3, 6, 7. Because 3 and 6 equal to 2, 3 and 6 and 7 also are equal to 2, is equal to 2. So here we have in this from 0 to 2, from 0 to 2, from element 0 to element 2, we have 2 subsequences which their n bitwise equal to 2. For 3, we have also 2, which are 3 and 3, 7, because the 3 and 7 is equal to 3. So here, from 0 to 2, we have 2 subsequences, which their n bitwise is equal to 2. For 9, 5, 9, 4, 6 now. For 6, we have also 2, which are 6. We have found it previously, and 6, 7 from 0 to 2. Let me see. For 7, we have only one, which is 7, this one. So, what we can say here, how to compute the result? We have k is equal to 2. So we check. We're going to compute the number of subsequences that have exactly 2 set bits in their bitwise and values binding. We have to check in this result from 0 to 7, which result has k set bits, which is 2 set bits, which is 3 and 6. So we're going to take this value at the end of on the last row, 2 and 2. So the final result is equal to 2, is equal to 4. Okay. So we're going to use the dynamic programming method technique, where dpij is equal to the number of subsequences from 0 to I, such as their n bitwise is equal to j. This is very important here. As you see here in the table, in each cell, for example, let's take this one, which mean 2 here, which means 2. 2 means that from 0 to 2, here from 0 to 2, we have 2 subsequences which their n bitwise is equal to 6. Okay. Let's see how all of this stuff will be computed. Don't forget that dpij is the number of subsequences from 0 to I, such as their n bitwise equal to j. We take the first portion from 0 to 0. From 0 to 0, we have only one subsequence, which is 3 from 3 here. Its n bitwise result is equal to 3. So we can put 1 here. It makes sense because we have only in subsequence of 3. Its n bitwise is equal to 3. So we have just one subsequence, which its n bitwise is equal to 3. All the others are 0 because there are no subsequence here at the moment, which is equal to 0 or 1 or 2 or 4 or 5, 6 or 7. Okay. Let's take now from 0 to 1, which is a 3 and 6. There are all these subsequences. So we can use dynamic programming to compute the number of subsequences which the result are 0 or 1 or 2, 3, 4, 5, 6 or 7. How it works? We're going to take for every cell here, we're going to take the previous result. For example, this one will take 0 here, the previous result for this column. And we check if there is previous subsequences which their n bitwise is equal to 0. Same for 0 and 6. Because here we have the result 0, we're going to check if there is a subsequences which n bitwise equal to 0 and 6. There is no subsequences which the result n bitwise is equal to 0 and 6, which is 0. So it remains 0 here. And this one, we take the previous one. There is no previous subsequences which their n bitwise equal to 1. Same for 1 and 6. We take the previous result. There is no previous subsequences which their n bitwise is equal to 2. Same for 2 and 6. We take the previous result here because we have a subsequence, a previous subsequence, which its n bitwise is equal to 3. Now we're going to check 3 and 6. 3 and 6 equal to 2. So we're going to fill the P, the 1, 3 and 6, which is 2. Which is equal to the result of the current result at the P 1, 2, which is this one. This is the current result, which is 0 here, plus the previous result in the previous subsequences, which its n bitwise is equal to 1, which is at the P0. Okay, so which is equal to this one. Take from this one. Okay. Because we have a subsequence with the 3. So we're going to check 3 and 6. This one is equal to 1 here. So 0 plus 1 is equal to 1. So we're going to put 1. This one, because we have a subsequence 3, 6, which its n bitwise is equal to 2. For here, for 4, there is no previous subsequences, which their n bitwise is equal to 4. So same for 4 and 6. Same here. There is no previous subsequences, which the result equal to 5. Same for 5 and 6. Same here. There is no previous subsequences, which the result equal to 6. Same for 6 and 6. So here we're going to check the previous subsequence, the previous subsequences, which the result is equal to 6 previous, not current, previous. That's why we have 0. Same for 6 and 6. Same for 7. There is no previous subsequences, which the result is equal to, and bitwise is equal to 7. Same for 7 and 6. You can tell me now, we have 6 here. Each and bitwise is equal to 6. So we have to have 1 here. So at the end of this column, finish with this row, sorry, at the end, when we finish with this row, we add 1. What about 6? So dp 6, this 1, is equal to, its and bitwise is equal to 6, so we put 1 back. Okay. So, of course, for 3 here, there is 1 subsequence for 3 in yellow here, in this row. There is 1 subsequence in this row, which and bitwise is equal to 3. Go to the next row. Here, previous result is 0. There is no previous subsequences, which the and bitwise equal to 0. Same for 0 and 7 now, because we're going from 0 to 2 for now. We check all these all these elements, which all these subsequences are here, as you see. So same for 0 and 7. Okay. We're going to use the previous result, because in the previous result we have computed all the subsequences from 0 to 1. So now we add 2. Same here, there's no previous subsequences, which the and bitwise is equal to 1. Same for 1 and 7. Here we take the previous result, 1. The previous result is 1. We have 1 subsequence, which and bitwise is equal to 2, which is 3, 6 here. So we're going to check for 2 and 7. 2 here is the result of 3 and 6. 3 and 6. 3 and bitwise 6 is equal to 2. So we're going it's like we have said here. Check if we can add 7, 2, 3, and 6 to have the and bitwise is equal to 2. The total and bitwise of 3, 6, 7 is equal to 2. We have 3, 6. We end with 7. 3 and 6 is equal to 2. So we end with 7 here and check if we can have 2 and 7. 2 and 7 is equal, forget this, 0, 0, 0, 0, 1, 1, 0, 1, 0. We have 2. So dp 2 is equal to 1. To the current result at dp 2, which is, as you see here, is 1. It comes from the previous computation, previous result, plus 1, plus dp of dp 2, sorry here. Sorry guys for this. Here dp 2, because we are there 2, and this 2 came from 2 and 7. dp 2 is equal to the current result at dp 2, which is 1, yellow here, plus dp 1, previous result 1, 2, which is 1, 2. So at the end we will have here. This is obvious. This makes sense because the subsequences here, which their and bitwise is equal to 2, are 3 and 6. 3, 7, 6. Okay. We go to 3. Color here. Look here. We take the previous result, because in the previous result we have one subsequence which its and bitwise is equal to 3. This one, previously, this one. And we check 3 and 7. Okay, we have 3. Can we add 7 to the element 3? That and that such as its and bitwise is equal to 3. 3 and 7. 3 and 7. 0, 0, 1, 1, 0, 1, 1, 1, 0, which is 3. 3 and 7 is equal to 3. So dp2 3 is equal the current is equal to the current result at dp2 3, which is 1 here. All right. dp2 3 is equal to the current result at dp2 3, which is 1 here, plus dp, blue here, the previous result, which is at dp1 3, which is 1 here, this one. Okay, so 1 plus 1 is equal to 2. Makes sense? Because we have 2 subsequences which the and bitwise is equal to 3. This one and 3, 7. This one. Here now we have no previous subsequences which the and bitwise is equal to 4. So same for 4 and 7. We have no previous subsequences which their and bitwise is equal to 5. Same for 5 and 7. Okay. Here now, let's get this color. We have one previous subsequence which its and bitwise is equal to 6. Okay, equal to 6. Let's see for 6 and 7. 6 and 7, 0, 1, 1, 6, 0, 0, 1, 1, 7. Here we have 0, 1. We have 6. Okay. So dp2 6 is equal to dp, the current result at dp2 6 taken from the previous one, plus dp1 6, which means 1 plus 1, this one plus this one, which is 2 here. So we have 2. Makes sense because we have 2 subsequences which their and bitwise is equal to 6, which is 6, which are 6 and 6. Okay, we came here. There is no previous subsequence which its and bitwise is equal to 7. So same for 7 and 7. but we have 7 here. This one, color this one is 7. So at the end we have to add 1 here for that 7. This is how to fill this period. And as we have seen in the previous slide, we just only want to take only the result that have k set bits. Okay. For our example, k is equal to 2, which are 3. There is 3. This is the result of the AND bitwise, and 6. Yeah, 6 have 2 set bits. So we take this 2, 2 plus 2 is equal to 4. So for this array, we can make only 2 subsequences which their AND bitwise equal to 4. The general formula will be dp. Sorry for this. dp I j. First, we take the previous result. dp ij is equal to the current result at dp ij plus dp previous result is at I minus 1 j. Then we check for that j and the element at the position I. That result, that AND bitwise of the previous result, previous subsequences, and the current element is equal to the current result at that position j and ai plus the previous result, which is minus 1 j, as we have seen in the computation for this example. This is the pseudocode of the problem. As we have seen, we put a 1 at the first row for A0 because this is the first subsequence. So we have one subsequence that equal to 0, and we run over all the rows, and for each row we fill all the columns from 0 to 63 because we've seen on the problem statement all the element in the array are between 0 and 63. We take the previous result, we make and bitwise with that result j with the element at I, and we compute as we have seen in the presentation. At the end, we add 1 to the element at I for the element AI. We add 1 to it. This is the code in C++. This line here is to compute the final answer. As we have seen, we use only the last column, the last row, and the last row at n-1, and we check which result, which value here. This is the AND bitwise result is equal have k set bits. Okay. If yes, here if there's AND bitwise which have k set bits, we take this value here as the at the last row, and you add it to the answer.